Get to the last conic section, and that's in 12.4, and it's something called an ellipse. And what I'm going to do is I'm going to go to the textbook where the definition is given. This requires more algebra. I could do it, but it's just gonna, I know I'll lose you, but I want to show you where it is. You should be able to follow the algebra that's in the textbook. Let me take you through that. How do we start? We start all these things with a word definition. So a word definition of what does it mean to be an ellipse? And this is an ellipse in the plane. I'm going to come over here and share the screen over here. So here's our definition of our ellipse. Yeah, an ellipse is the focus of all points in a plane such that the sum of the distances from two fixed points remain constant. The two fixed points are called the foci of the ellipse. So here's my focus 1, focus 2. So the distance, and what I have is distance 1, and there's my point, and distance 2. So this distance is a constant. So the distance 1 plus distance 2 remains a constant. So here it is, d1 plus d2 is constant. Okay, so now let's turn that from this word and picture description into something we can calculate with. So what do? We overlay that with a Cartesian coordinate system. And what we're going to do is we're going to identify the center of that ellipse, and that's going to be identified as the origin. I mean, we'll show how to expand it later on and extend it, but this is the easiest way to start. So here we put our little Cartesian coordinate system over that picture, and we put the center of that ellipse here. And with that, we'll also define, some coordinates for these various things. So we'll say this focus over here is at negative c comma 0. This focus over here is positive c comma 0. There's a symmetry in this. And I'm going to say that this, where the ellipse crosses the x-axis on the left-hand side, we'll call that at x equals to negative a, and obviously y is 0 because it's an x-intercept. And the other x-intercept is at positive a comma 0. So we kind of give these names over here. Now, we set this up in a very specific way. There are two axes here. There's the horizontal and the vertical. The axis that captures the longer part of the ellipse, that is called the major axis. So for now, we're doing an ellipse who has a major axis along the x-axis. Very shortly, we'll switch it up and flip it the other way. The other axis is called the minor axis. So this is set up to solve something where a major axis is along the x-axis and whose minor axis is along the y-axis. Major means it's more spread out over here. Minor, it's more kind of pushed down. It's pushed down along its kind of think of it taking a circle and you squash it down along the vertical axis and you stretch it out along the horizontal axis. Horizontal in that case is major, vertical is the minor axis. Okay, so what do? Well, this is the distance 1 and the distance 2. We go right to our distance formula, just like we did for the circle and the parabola. So distance 1 is here's a point x comma y, and I take my x minus this x1, which is in this, or this case, it's negative of negative c, and then y minus 0. So I get x plus c squared plus y squared quantity square root. Distance 2 is done in a similar way. And I do the same sort of thing. Now it's this point to that point, where c now is a positive in front of it, and then we end up with x minus c and then y squared. Okay, so we want distance 1 plus distance 2 to be a constant. Now it turns out to make this a little bit easier, or get a nice formula in the end, not so much easier, but formula in the end, instead of setting it to a constant a, we'll arbitrarily set it for 2a. That's only, initially it was set to a, and then someone figured out, oh, well, the end formula is nicer if I choose it to be a rather than 2a. This was just an arbitrary thing. It's still a constant. A is a constant, but by putting a 2 in front of it, your final form is going to work out nicely. So here I do. I take my distance 1 plus distance 2 is that plus that is equal to 2a. Now, the part on the right here, I'd like to kind of, get rid of all those radicals. We want to simplify this into an expression without radicals. So what do? First thing you can do is move one of the radicals over. We chose over here to move the square root of x minus c squared plus y squared to the right-hand side. So now if I square both sides, I get rid of the radical on the left-hand side, just gives me the radicand. This, when I square it, it still doesn't get rid of the radical, but it will allow me to do something. So I square this out, and I get the following. I still have a radical in the middle. So what do? Step by step, I use the algebra. Well, first off, I can cancel things out over here. There's x squared, there's a c squared. Things start to cancel out, if you will. There's a c squared plus y squared, c squared plus y squared, that cancels out. So on this left-hand side, I have 2cx. And then what I'm going to do is I'm going to swap. I'm going to bring the square root on this side. And then I'm going to move the 2cx onto the right-hand side. So on the right-hand side, I end up with 4a squared minus 2cx minus 2cx. So that gives me negative 4cx. Okay, next step over here, I can divide everything by 4. So I can divide everything by 4, and what happens? 4's go out. Now I can get rid of the second radical by squaring both sides. That a turns into an a squared, the radical vanishes, and I have the following when I square this out. So now I work through this a little bit. So I multiply everything through by the a squared, kind of multiply everything, and then I start getting some cancellations. A minus 2c times a squared, and a minus 2c times a squared x on both sides, they cancel out. So I get the following. I have a squared, x squared plus a squared, c squared plus a squared, etc. Well, over here I have another x squared term, so I can move that to the left-hand side with a negative in front of, if you will, the a squared, and then I factor it out. So the x squared term has an a squared minus c squared times x squared. And then on the left-hand side, I just leave the a squared right there. And on the right-hand side, when I kind of move everything over, because I have to move the a squared c squared over to the other side, factor out an a squared, I have the following. Now my last step over here is I'm going to divide both sides by the coefficient in front of that x squared term. So over here, by a squared, by everything on the right-hand side. I'm going to divide everything over here by my a squared times a squared minus c squared, left and right. So the a squared minus c squared cancels, and then the a squared stays in the denominator. Over here, the a squared cancels, and what I have in the denominator is just a squared minus c squared, equal to 1. Now, if we let a squared minus c squared, we know that can be a b squared. Why can we do that? Well, if you look back at the picture, you can see right over here that a is greater than c. This focus is inside the ellipse, and the vertex on the major axis is larger. So a squared minus c squared is a positive quantity. If it turned out to be negative, I couldn't set it to a square term, but I can. So we're arbitrarily going to call this something called b squared, and this is going to be our standard equation of an ellipse. So let me kind of go to that. You can go through it again step by step, but I didn't want to put all the algebra like that in front of you. So here's our standard equation for an ellipse. Ellipse. Centered at the origin. And major axis along the x-axis. Major axis on the x-axis. Now, it looks like this. I have my x squared over a squared plus my y squared over b squared is equal to 1, where b squared is smaller than a. It's a squared minus c squared. And this is giving us, here we're centered at the origin. And this is my, a comma 0 minus a comma 0. And here are my two c's. So this is minus c comma 0, focus 1, and focus 2, plus c comma 0. Now, what does that b value equal? Well, if I simply set x equal to 0 over here, so there's my x value. If I set x equal to 0 and I solve that, what do I get? So let x equal to 0. So I'm looking for the y-intercepts. So I get y squared over b squared is equal to 1, or y squared is equal to b squared. Taking the square root, I get y is equal to plus or minus b. What does that give me? It gives me my locations of the point on the minor axis. So this is at x is 0, y is plus b, x is 0, y is minus b. So that gives a physical meaning to what the b is over here. It's where my ellipse will intersect the y-axis, my two y-intercepts of that relation. Okay, so that's what we have. So what do we want to do? Well, we want to characterize this. So the objective is to characterize an ellipse. Is to characterize, that's how we analyze it, by characterizing it, an ellipse. What do? Well, we like to find the foci. That's one thing we need to do. We're assuming that, again, centered at the origin. I'll put the equation for when it's not centered at the origin and just kind of show you what it is. So find the foci. The other thing you want to find, both the intersection points on the major axis. Find the, x-intercepts, which are the vertices on along the x-axis, the x-intercepts, or the vertices on the major axis, and find the y-intercepts too, which are the vertices on the y-axis. It's kind of like, that's kind of similar to a vertex. It kind of does the same sort of thing. Find the y-intercept, which is similar to finding vertices on the minor axis. So what are we actually finding? Well, we're finding the C here, the A here, and the B here. That's what we're finding. The ABCs of ellipses. Okay, so let's take a look at some examples on how we do that. But I guess before we'll do that, let me show if I remove the restriction of being centered out of the origin. We're not going to cover this, but I just thought I'd show you it's still the same process that we do over and over again. So here's a new form of the standard equation with center at h comma k. So the standard form again, it's also at the minor axis on the x-axis, but or not on the x, but parallel to the x-axis, with center at h comma k. So what would it look like? As long as my center is on my major axis is on the horizontal, it'll look like this: x minus h quantities squared over a squared plus y minus k quantities squared over b squared equal to 1. Notice we have a 1 on this side. And we have b squared is equal to a squared minus c squared. So if you, later on, it's another course, if you want to move that ellipse away from the origin of the center and move it to some point h comma k in the xy plane, that's the form you would take. Okay, so I just wanted to write that just so you have seen it. We do that in all sorts of things. It's always x minus the point and y minus the point in any formula we have. So there's a formula for a line, formula for a parabola, formula for an ellipse, for hyperbolas, everything kind of works the same way. Let's take a look at an example of how we go about working this. So what I want to do is do this example which says, let's analyze this ellipse. So we want to find those features. Let's analyze it, what we have. So here's an example. Analyze the ellipse given by the information x squared over 25 plus y squared over 9 is equal to 1. Relatively simple one. Now, should point out, when you're given it with a 1 on the right-hand side here, even if there's not a 1, but the value of the variable that has the largest number, that tells me that my major axis is along the x. The smallest number is always along the y. 25 is larger than 9. So what do? I put it into my standard form. This is centered not at the point h comma k, it's centered at the origin. So it's equivalent to x squared over 5 squared plus y squared over 3 squared is equal to 1. Well, this tells me right away that my a is 5 and my b is 3. So I can, go right to, let's also graph it so we can see what's happening over here. So along the A, 1, 2, 3, 4, 5, that's a point on it. 1, 2, 3, 4, minus 5, point over here. Over here, 1, 2, 3, that's my other vertex along the minor axis. And over here, minus 1, 2, 3 as well. Almost done up here. Now, what I also need, I have the two where they are. I could draw a picture of it. It's not going to be as accurate until I find the foci, but you can just kind of estimate. It's going to kind of have a football appearance over here. It's an ellipse. It's like a cross section of a football. But I'm still missing C. So I need to find the two foci that are on the major axis. So how do I find the foci? Okay, I go with the relationship that's valid for this, is valid for that, which is my b squared, b squared is a squared minus c squared. So plug it in, so I get 9, right, is equal to 25 minus c squared. Now what do I need to do? Solve that for c. So I'll add c squared for both sides, and then I will subtract off 9. So I get c squared is equal to 16, because 25 minus 9 is 16, or c is equal to plus or minus 4. So now I can place my foci on my graph. So I go 1, 2, 3, 4. There's one of my foci, negative 4, comma 0. And here's the other one over here, is my positive 4, comma 0. So those are the foci 1 and foci 2. That's it. We know everything that we need to know about that ellipse. Didn't have to do a lot of work. This was an easy one. Not a lot of work had to be done. Okay, so let's step it up a little bit more now and look at another example. It's just finding your A, B, and C and knowing what A, B, and C represent, and that should make it relatively easy. It's just the ABCs of ellipses. So let's take a look at another example. Now it's not given in exactly the same way. So here's the same idea of analyze the ellipse given by this relationship. 9x squared plus 4y squared minus 144 equal to 0. Okay, so now they gave us something a little bit different over here. So what we'd like to do is put this in standard form. So first thing I'm going to do is let's move the 144 over. So I take my 9x squared plus 4y squared is equal to 144. So the next thing I'd like to do is I'd like to get a 1 on this side of the equation. Remember, that's what my standard form is. So I want to divide that by everything by 144. Because remember, here's my standard form. X squared over a squared plus y squared over b squared is equal to 1. So let's divide everything here by 144. Okay, so when I do that, I can do it term by term. So I have 9. Let's just rewrite 9 as 3 squared. We can see some square things going over here. So if I turn around and just let 9, or I could actually 9 going into, if I wanted to, I could divide those. Let's just write that out that way. So I'll take my 9x squared over 144 plus a 4y squared over 144 is equal to 1. Well, 9 goes into 144 because, take a look at this. 144 is 12 squared, so it's 12 times 12, which is 3 times 4 times 3 times 4, which is 9 times 16. So 144 is equal to 9 times 16. So the 9's cancel out to give me x squared over 16. And then we also have over here that if I look at this one over here and one of the 4's cancel out over here. So I have one of the 4's and I have 9 times 4, I get 36. So 4 over 144 is plus y squared over 36. Okay, something changed here. In this case, the larger number is under the y squared. So that means my major and minor axes have just switched on me. Instead of having my major axis along the x, it's now along the y. So I should really be comparing it instead of to this, y squared, there's my y squared is a squared, plus x squared over b squared is equal to 1. Whatever number here is larger, that is your, when it's in this form, and they've all divided out, that is your, in this case, my major axis. Notice the coefficient in front, that was larger, but when I divided, that became larger. So I switched. So instead of going this way, I'm now going this way. So this is kind of my a and minus a, this is my b and minus b, and this is my major axis. Because that's my major axis. So you have to look at that when you're analyzing it. Okay, so let me continue to write this. It's just x squared over 4 squared plus y squared over 6 squared is equal to 1. So we're going to analyze it. So let's find the vertices and everything else. So I determined that my major axis was along the y because the largest number here is under the y square term. So I know I'm working with something like this. So let's put it around this way. So let's just rewrite it. So I'll put my y squared over 6 squared plus my x squared over 4 squared is equal to 1. Now it tells me my a is 6. My b is 4. Now c squared, well, b squared is equal to a squared minus c squared. It's the same, it just switches to the other axis. And so I have my b squared is 16 is equal to 36 minus c squared. So bring this over and bring that, kind of swap these two from one side to the other. So I get c squared is 36 minus 16, or c squared is equal to 20. And that determines, and I can say that C is equal to plus or minus the square root of 20. But I can simplify that a little bit. I can bring a 4 out of the 20. 4 times 5 is 20. 4 comes out of the square root as a 2. So it's plus or minus 2 square roots of 5. Okay, so let's draw a little picture of this now. So over here, I come this way. There's my x, there's my y. So coming over here, there's my one vertex there, and that is that x being 0, y is 6. Here's my other vertex, 0, comma, negative 6. Along this way, I have 3, comma, 0, and then over here, I have a minus 3, comma, 0. Now, I could kind of, from that, it's not, I don't have it grid too well, but it's something like this. But we still want to find and at least plant and draw where the foci are. Be a little bit rounded, if you will. Now let's identify the foci. Well, we can see, get a numerical value, so 2 times the square root of 5 gives me a value at 4.47. So I go over here and 1, 2, 3, 4 and a half, right about there. And that's my foci, and that has coordinates of 0, comma, 2 square roots of 5. And I go 1, 2, 3, 4 and a half, 4.47 to be a little more, precise. And that's it, gives me 0, comma, minus 2 square roots of 5. And I call it, doesn't matter. That one's focus 1, and there's my focus 2. And that's how I analyze this particular ellipse. You either have a major or minor axis there. Yes, Kyle. The question?
Hey, yeah, where did you get the 3 from on the x-axis?
Oh, that's my mistake. That's 4. Excuse me, yeah. I was back in the other one. I'm kind of going on autopilot. Keep me awake there. That was autopilot doing me. I was still looking at the other problem in my head. Yep, keep me awake there. Keep me awake. It comes around to plus or minus 4, not plus or minus 3. Yeah, there we go. A little bit better. There we go. That's good. Keep me awake there. So it's a square root over here, so it should be 4. That's why I didn't plot it there, but my mind was still on the other problem. I didn't look back. And it should be my C value. And what I do is I usually put this in the calculator, and I get approximately, so I know where I can put it exactly, plus or minus, in this case, 4.47, etc. So I said roughly 4.5. 1, 2, 3, 4.5. Then I write the exact coordinates there. So that's my ellipse in that way. So those are the 2 major types of problems that you have with ellipses. Or one of the major types of problems is you want to put it in standard form and then identify the A, B, and the C. Okay, that's one type of problem. Now, there is another type of problem with ellipses, and that's by giving some verbal information and then being asked to come up with the actual standard form of that. So let's kind of give some verbal information and look at this second type of problem, the third example. I gave 2 examples of the first type, and now we're going to do 1 example of the second type. Now, I should mention the reason we chose that distance to be 2a was so that we would have this be a squared instead of a over 2 quantity squared. That would have been nastier. So we chose that distance to be 2a to make this a nice simple a squared. That's why we chose a funky constant there. It just makes the final form a lot easier. I could have left it as an A, and that would have been kind of crazy. So from knowledge of how things work, we're able to make it look a little nicer in the end. Okay, this is a third example, but the second type of problem that you often see with these. So here's example 3. And again, you want to analyze the ellipse, and that means find the ABCs. With the given information now, and this is it. Whose center is at the origin, that's only ones we're going to be working. Whose center is at the origin. And it passes through the points, and passing through 2 points. And passing through 2 points. And I'm going to give their coordinates. And one coordinate is going to be 6, 1, and the other coordinate is going to be 2, 3. So what I would do is start to sketch it, give an idea. I'm going to have to choose my major and minor axes over here. So let's come over here and center it at the origin, so it's symmetric about that. And let's do both of those, 6, 1. And here's 1. It passes through this point right here. And then in addition, it's going to pass through the point 2, 3. So 2, 3. Okay, so we don't know where anything is other than that. That's everything we're given. We want this thing to be centered about the origin over here. Let me put my X and Y over here. And see how we go about doing it. So what we can see, though, in this case, we know that the major axis has to be along the x-axis. Just from this picture, I can't suddenly shoot up there and make that larger. So this tells us from this, the major axis is the x-axis. Okay, why is that important? Well, it tells us that my general form is x squared over a squared, where a is the larger number, plus y squared over b squared is equal to 1. So that's what we get from plotting those points. My major axis, if it was inverted, if it's 1, 6, 3, 2, my major axis would have been along the y-axis, and I would have put the y squared over the a squared. So that's the difference. Okay, so now what do? Well, I have to find my a and b. And then my a and b, I can always find my c by using a squared minus my c by using the relationship b squared is a squared minus c squared. So how do we do this? Well, let's plug it in and see what we get. So I'm going to take that same formula. I'm going to replace x with 6, y with 1. So I get x squared, which is 6 squared over a squared, plus, in this case, my y squared, which is 1 over here. Every point on that graph has to satisfy this equation. So I get my 1 squared over my b squared, and that has to equal my 1. So I get 36 over a squared plus 1 over b squared has to equal 1. That's to that point. Let's do the same thing for this one. I'm going to replace x with 2, so I'm going to get 2 squared over a squared. Plus, well, I'm going to square the 3 and get 9 over b squared. I'll write it as 3 squared. Just so you can see, 9. Is equal to 1. Or I get 4 over a squared plus 9 over b squared is equal to 1. This is a nonlinear system of equations. Now, if we wanted to, we could actually put this into Desmos and find the answer, but I want to do this algebraically. Okay, I come over here and work this now. What I would do, more than likely, is I would multiply both sides by a squared b squared. Just clear out this out. So I'd multiply this by a squared times b squared. So I get my 36b squared plus my a squared is equal to a squared b squared. Same thing here. I get my 4b squared plus 9a squared is equal to a squared b squared. Okay, what I notice here is that the right-hand sides of both are equal. They're a squared b squared, so I could set them equal to each other. So combining these together, I get 36b squared plus a squared is equal to a squared b squared, which is actually equal to this. It's equal to 4b squared plus 9a squared. I got rid of the common right-hand side by setting them equal to each other. Why did I do that? Well, I can simplify this a little bit. So I can turn around and subtract 4b squared, and I can subtract 1a squared. So doing that, I end up with 32b squared, so 36 minus 4 is equal to 8a squared. Now, I could divide both sides by 8 if I wanted to. Just makes it a little bit easier to work with it. Don't have to, but it's easy to work with if you do that. So this tells me my 4b squared is equal to a squared. Okay, that's a relationship that I have, an important relationship. Well, what can I do with that? Well, I can actually use it into either one of those and replace everywhere I have an a squared, I can replace it with a 4b squared. It doesn't matter. Let's do it right here, the easier one over here. So this is the equation here. I'm going to use that first equation and replace for a squared in this equation. 36b squared plus a squared, but a squared is 4b squared. I just found this 4b squared is equal to, in this case, a squared, which is 4b squared. So here it is. My a squared is 4b squared. So 4b squared, that's my a squared, times my b squared. So notice this is the relationship just in terms of b squared. What I can do is just divide everything by 4b squared. Well, let's combine those first. Let's do it over here. So over here, I can now, 36 and 4 gives me 40b squared is equal to 4b to the 4th. Divide everything by 4, and I get 10. Well, divide everything by 4b squared. So I'm going to divide, let's do it so I can show you. 4 times b squared, 4 times b squared. So this gives me 10 is equal to b squared. The numbers are not perfect and nice, but it tells me what b is. This tells me b is plus or minus the square root of 10. So that gives me some information to go there. Now, what can I do with that? Well, I can come over here and figure out what a is. Okay, so now I know what b, I know if I go over here, square root of 10, let's just get the decimal approximation for that. That's 3.16, so here's 3.16, it's right about here. And then the negative one as well. 3.16 is the other value right here. There's my minor axis values. So 0, comma, square root of 10, 0, comma, minus square root of 10. So I'm starting to get its vertices. Now what do I do with this right here? Well, I use this, and it goes right in over here to my b squared. So b squared is just 10. So now I do that, I get 10, well, excuse me, 4 times 10, b squared is 10, is equal to a squared. Well, 4 times 10 is 40, is equal to a squared. Then tells me that a is plus or minus the square root of 40. Well, if I wanted to, I can bring a 4 out, so that's equal to 2 plus or minus 2 square roots of 10. So it's kind of double that, so that was like 3.16. So double that gives me 6.3 over here. So it's actually this value over here is 7, so it's about a third of the way down around over here. And that is my x coordinate is 2 square roots of 10, comma 0. And then over here, let's see if I'll get rid of some of this, so at least we can see our graph over here a little bit better. To be able to put everything on the same board over here as best we could. So a third of the way over here, so it's right about here. And that's equal to a minus 2 square roots of 10, comma 0. And then we can just draw our, so I have A and B. I'm still not done. Got to go through that point. It's got to go through that point. It should do this. Okay, so I have my vertices here, but I'm still missing my C value. Where do I put the foci over here? So let's see, how do we, why don't you try that? I know what b squared is, I know what a squared is. Can you solve for c squared? Because a squared is 40, b squared is 10. So solve for c squared. Let's see what you get. So sometimes the answers don't turn out to be nice numbers. More often than not, these things are not perfect. They're perfect in their shape and form, but where they're located could be any real number. So if we're doing that, hopefully everyone sees that c is plus or minus the two values for the foci of the square root of 30. And roughly about 5.47. So over here, 1, 2, 3, 4, 5, right about here. 1, 2, 3, 4, 5, and almost halfway there. So it's minus the square root of 30, comma 0, plus the square root of 30, comma 0. Now, does anyone want to see how I got c equal to the square root of 30? Is everyone okay with that? I'm just solving b squared, we got is 10. A squared is 40 minus c squared. So move the c squared over, subtract the 10, I get c squared is equal to 30, and then I simply take the square root. So I've analyzed that ellipse. I found all its ABCs, its foci, and where it intersects. It's two vertices along the major axis and two vertices along the minor axis over here. I knew this was a major axis. Now, if I switched it around and called this b squared and that a squared, it wouldn't have worked out nicely. Things would have been funky over here. So if you go down the wrong path, it's going to say that is impossible. But I can't have, because this is going to get contradictory things. You're going to have squares equal to negatives. So it will suddenly give you junk. If you suddenly start solving this and garbage is coming out, double check this first step where we chose the form in this type. Instead of the y squared over a squared, we chose the x squared over a squared, because that was our major axis that we discovered there. Okay, so those are the sorts of problems when you analyze an ellipse. It's the ABCs of an ellipse. So we have a few minutes left today. I want to